In our last video, we talked about the square Euclidean distance, which is a measure of dissimilarity used in machine learning for clustering algorithms like k-means. So the square Euclidean distance between the 2 points x and y in d-dimensional space is calculated by just summing the squares of the distances between the corresponding coordinates x and y. So let me try to demonstrate how this distance can be represented in one-dimensional, two-dimensional, and three-dimensional spaces. First, let's look at the 1D space. We plot 2 points on a number line and the square Euclidean distance. So they have 2 points x and y, which plotted on a line, and the dashed line represents the distance between these points, and the square distance is the squares of this length. In a 2D space, we plot 2 points in a plane and visualize the square distances in this area of the square, which forming a line connecting these points and the axis. The 2 points are plotted in a plane, and the gray dashed line connecting these points both directly to its projection on the axis, which forming a right triangle. So this square distance is calculated by squaring the lengths of both legs of this triangle and by adding them, which can be conceptualized as the area of the square form if you imagine extending its legs. And then we plot 2 points in three-dimensional space. We visually represent the square distance concept. The points are positioned in three-dimensional space, and the lines connecting these points creating a spatial path. The concept of the square distance extends to the third dimension, which incorporating with the vertical z-axis difference squares, which along with the horizontal difference. This visualization demonstrates how the square Euclidean distance or dissimilarity increases with the separation of the points across 1, 2, or even 3 dimensions respectively. So this is a fundamental concept which is used in the clustering method to gauge how alike or unlike the data points are based on the positional differences. Let's try to calculate the square Euclidean distance between 2 points x and y in d-dimensional space. In our this example specific case, we use k is 2, so the formula is effectively sum of the squares of the distance between the corresponding components of the vector x and vector y. In this 2D space, we can think of the point x1, x2 and the point y1, y2 as 2 points on the Cartesian plane. So the square difference between the x1, y1 and the square difference between the x2, y2 measure the square distances between these points along the x and y axis respectively. So we already visualized this function over a range of values for x and y, and then we fixed the point y on 0, 0, and then we vary the x over a grid of values on this plane. So this gave us a graph which shows how distance from the origin to each point x changes, and the range of the x1 and x2's value is from -5 to +5. So this is the function of the coordinates x1 and x2 with the point y fixed at the origin 0, 0, and the color scale indicates the distance value, with the lighter colors representing the small distances and the darker color indicating greater distances. So as we expected, the distance increases as we move away from the origin, which is showing that the delta of x and y capture the square of the Euclidean distance from any points x1 and x2 to the origin in this 2D plane. Let's try to illustrate the square Euclidean distances from the fixed point y, which is 1, 1, 1, in a three-dimensional space. Well, the x value is vary across a grid. So each point in this plot represents a different coordinate, which is x1, x2, and x3, and the color, which indicates the square Euclidean distance to the point y. The color gradient, which is a transition from purple to yellow, shows the increase in distance. For example, the yellow points are closer to the point y, and the purple points are farther away. So this visual representation effectively demonstrates how distance changes as we move away from a fixed point in a 3D space.